All right, so let's get started. All right, so the homework 5 is listed to be due on Wednesday. So let's get who's finished it already? Okay, and who feels like they're easily on pace to finish it by Wednesday, and who's not? Okay. So I'm open to an extension on this homework. That seems like that'd be popular. So I also I feel bad kind of putting it too close to the final report. So when would be a good time for an extension to be due? Is like Friday night a good time, or do you guys like, no, not Friday night, that'll ruin my Friday night?
What about like Monday? Like Monday before class?
It's like Monday before class. Is that a good time? You guys want the weekend to do it? Yeah. So okay. So let's do a show of hand votes. Who would like it to be due Monday at say 2:45? And who'd rather have the same deadline as now? Okay. So I will make this extension official on Canvas after class. Okay, so that's fine. I kind of expected that, but I didn't want to list it too early as being due then, so you've hopefully at least started on it by now, so it's not too close to the final report. All right. Okay, that sounds good. All right. All right. So we're gonna. Oh, I have. So one more announcement before we get started. And then we'll look back at the schedule. So there's a meeting of the data science club. It's going to be tomorrow. That's Tuesday. Would be April 3 at 5 p.m. Okay, and so this is going to be a presentation by a data science so from Adobe. If you don't know, Adobe has got a huge operation in Lehigh where they do lots of like web analytics stuff. And so it should be a cool demo of like learning market segments, and importantly, there should be some pizza. Okay, so if you're hard at work, if you're around, and you want to learn something and get some pizza around 5 p.m., I think it's in Web 1230. Okay, so an upper part of Web. Okay, so it should be a cool thing. How many of you are subscribed to the Data Science Club mailing list with all these announcements on it? Okay, and some of you haven't subscribed to that yet. Okay, but it's easy to subscribe. It's not too heavy of the traffic list. I suggest you all subscribe to this. All right. Okay, so let's look back at the schedule. Okay, so your final reports are coming up in, what is this, in like 2 weeks. Okay, so I had meetings, I think, with all of the groups last week. If you have follow-up questions, I know they were kind of short things. Feel free to email me or stop by office hours, come ask me, or just, I'm happy to continue getting feedback to get your reports ready. As it gets closer, I'll try and make some general comments about kind of what I would like to see in the final report and how it's structured, but if you look at the actual PDF, it's got some instructions in there as well to help you, to try and help guide you. All right, so then we're going to have 2 lectures this week on kind of noise and privacy and issues with kind of dealing with some of the messy parts of data. And so then we'll move into some graph analysis there. And I'll try and release the homework assignment, the last one for graphs, which will again be short. I think you'll basically have all, if not most, of what you need for it after this lecture. I'll try and release it around then, if not earlier. And it's due kind of the Monday after the last day of class, which is the end term. Okay. All right. All right, so let's talk about some noise in data. And, right. And so, let's see, so noise is a very, so noise, and this lecture and the one Wednesday, I think, are going to be much more kind of coverage of kind of more philosophical than driven by the techniques like a lot of lectures. And so I hope you'll kind of, you're always welcome to interrupt and ask comments, but also kind of give thoughts on stuff. So hopefully more so than even in other lectures. So noise in data is what really makes data mining interesting, right? So if we're trying to fit some linear model through data, and the data looks like this, and there's a line which basically goes through all the data points, then this problem is trivial, right? I can, instead of doing this, I could have done, instead of doing an ordinary least squares fit, I could have done anything that was almost as stupid as picking, say, 2 random points and drawing a line through those and saying this is my model. It probably would have worked just as well, right? So it's the fact that there is noise in data which makes everything challenging, right? And it's also kind of the it's a bit hard to describe what is noise and how to deal with it until we know this kind of array of techniques in order for just to deal with noise. So I want to start by kind of trying to categorize what are the types of what are the main like the main types of noise. So I like to kind of say there are 3 different types. So there are things like spurious readings, and this is basically if you have outliers. Okay, so this could be you're recording, someone's typing in data by hand. This used to be more common, and they mistyped a number, or they added some extra zeros, and you have something that just doesn't fit with everything else. It could also be that you have an automated sensor, right? You have something like on a robot saying how far away is a tree, and it hits some particle in the air, and it bounces back and gives something much closer. Or there's something that comes into the sensor at a weird angle, and you get a reading that's much further away than it should be, right? You can think of, it could come from the measurement error as well. It could be a bug in the collection technique, or there's someone adversarially trying to, on some web forms, typing in nonsense or trying to mess with your analysis. These are things that are very far from trying to fit the model. And if everything looks like this, you're hopeless, but if you have a small number of them, you should generally be okay. And we've talked about, and I'll review techniques to kind of deal with these various approaches. Okay. But these are things that, like, this would be kind of, if I did, this would be type 1. Something very far away from the models. It's just, maybe it's even nonsense. Okay? And then so I'll say the second type is like the measurement error. So this is kind of like just regular noise. Like if I'm counting the average height of the students in the class, and only the people who are in class today are measured, I'm going to get a slightly different answer because not everyone is here in class today, right? If I'm looking at the population of every county in Utah, and I send out a form and I return something back, not everyone is going to reply. Some people will reply incorrectly, but the numbers should be pretty close to what they should be, right? So this sort of noise would be like, instead of the blue dots here, I could have more noise, and it could be like this, but hopefully this is going to be, you know, this would be type 2. This stuff is hopefully unbiased, right? It's some kind of maybe evenly distributed noise. Maybe the process it goes through introduces bias, but hopefully this is not adding bias into the data. It's just stuff that I didn't get the exact value, right? Maybe there's rounding error, something as benign as that. The model should hopefully, almost any model I use should be really good at this type of error, right? If I'm doing, you can go through, you can build up most of the machinery from a Bayesian perspective, where you assume data has some Gaussian noise to it, and kind of this is the sort of noise that this is assuming. Anytime you get a least squares error, there's usually some Bayesian with Gaussian noise interpretation, and this kind of would be like that Gaussian noise around what the true value is. Okay, and then the kind of the third main category is kind of is like the is data from the background, or is like some missing data. Okay, so for instance, the missing data will materialize in like a regression problem where say this is higher dimensions, and say for some of the data points, or maybe a lot of the data points, one of the dimensions is missing, right? Or I have a recommendation system where I have a bunch of people recommend different movies, but they only recommend a subset of the movies. We haven't talked about this sort of technique in the class so much. At a high level, what the general ideas are to deal with this is to try and is to try and find kind of like an average of all of the data that you did see, maybe with respect to the model, and then you can pretend like either center the data so those other parts you can set them to 0 if you don't know what they are, or to kind of or to kind of set them at the average value of everything else in some reasonable way, is the rough idea of what you can do here. Sometimes you can just only factor in the data, part of the data that you have into your analysis in a natural way. But this also fits in with things like, let's say that there's some, like there's this data which is, there's multiple dimensions going on here, right? And so the data that fits the model looks like has this pattern, but if you look in the other dimension of this data, in like this z dimension here, that in this z dimension, these data points are kind of spread out in a way that's random. So if you try and fit this dimension, it's not going to give you any signal here, right? So if you have really high dimensional data, you're going to have some of these dimensions that's just going to look like it's uncorrelated with the signal that you have. And so this whole dimension is essentially noise as far as the model is concerned. And then things like orthogonal matching pursuit and lasso, we're going to try and set the coefficients to this thing to be 0. And that's another way of getting away with noise, which is kind of orthogonal to these other measurement error and outlier based of these noisy models. Okay? So this is kind of a categorization of ways to think about different types of noise. The third type, you kind of need to come up with a specific approach to deal with these. There's these mechanisms to either fill in missing data or to try and filter out unwanted parts of the data in your analysis. The second type is what most of the algorithms are designed to deal with. This is the kind of the basic algorithms are designed to deal with the second type. The first technique, we're going to be hopeful some of the advanced techniques are going to deal with this. So if I add a regularization term in like regression, it should be meant to deal with this sort of noise. It should lessen the effects of outliers is one of the effects that regularization should have on the approach. I've also mentioned briefly these robust kind of statistics view. And this would be like, instead of minimizing the L2 error, the standard sum of squared errors, if you minimize the L1 error, the sum of the errors, this is going to tend to be more robust to outliers. So this is different from the regularizer, which could be L1. This is kind of just setting up the optimization problem that, in an L1. And these are often harder to solve, but there are ways to do them. They're often built into some languages, some packages. For instance, if we did k-means clustering, this was minimizing the L2 error. If we do k-median clustering, this was minimizing the L1 error. The k-median formulation is much more robust to outliers. Okay, so if you have outliers, you're much more likely to assign a whole cluster on that outlier if it's the k-means formulation than you are if it's the k-median formulation. Okay. So these robust statistics kind of sometimes naturally deal with outliers. All right, so this is kind of categorization. The rest of this lecture will be focusing on two things. One is going to be cross-validation. And the other one will be explicit lead, say, handling of outliers. Okay, so there's these robust statistic version that should give you a model that's automatically resistant to outliers. But if you don't want to do it, I'll talk about some other techniques for kind of handling outliers. So kind of other approaches to deal with this, that they kind of integrate into the building of the model in some more complex way. Okay, but cross-validation, I want to spend more time on this. This is kind of more, I'd say, even more important. Yeah.
So I have a question about a certain type of data.
Yeah.
So I don't know if you're going to talk about this, but a lot of the times I see data really grouped around that XY intercept, which can really affect the regression. And so I wonder, when you're dealing with a lot of data that's in kind of zeros or near zero, is there a method to just kind of drop stuff like that out of the analysis? I guess it's not really an outlier problem, but it's kind of like an over noise problem based on too much data.
Yes, you're saying you have kind of the picture. Let's see if I can get this right. You have a picture, you're trying to say fit a regression, and your data has some data that kind of comes maybe like this, but then there's a ton of data that's like right here.
Yeah.
Or maybe even at the origin. Mm-hmm. Yeah, so, okay, so it could be that these are outliers, right? And that this is really what your data is. And if you want to fit a model that fits everything, you don't want to put too much weight into these anyways. Most of the data is not going to have any non-trivial x value, right? So trying to learn too much from these when 99% of your data here is kind of a fool's errand. Or you could just say predict, you enforce if the x-intercept is away from 0, or the y-intercept is away from 0, then you can say, well, I'm going to force the model to go through here, and then it's okay for this data, and it does something if it happens to be away from there. You could also segment your data into two parts and trying to fit something here and fit something else here based on some sort of clustering that takes advantage of this. Yeah, so those are kind of but if your data is all along here, and there's only a little bit coming away from there, then it's fitting a regression on just that part of the data and expecting it to handle everything it's probably not the right thing to do. At least not for this part of the data. Unless you can pull off this part of the data to deal with separately, then you shouldn't, you're kind of trying to force something onto what's not really there.
So for the third type, the missing data, so are we assume that the data missing is a key attribute, or that can be like unnecessary dimension?
Yeah, it could be. I mean, this is kind of like a very broad category. You know, I'm trying to categorize all types of noise here in 3 bullet points, and I'm not going to succeed. I'm sure you can come up with some types of noise which don't fit in any of these. Right, so that's kind of just trying to give you a sense of, like, this is I think a reasonable way to break it down into categories, and there are kind of different approaches to dealing with them. And there's a lot that could be fitting in this sort of category. Like they're different from the regular sort of noise which your fit model is fitting with, and they're different from outliers. This could be most of your data has this. But it's not really, your model's not addressing that sort of noise directly. You may need to do something else to deal with that.
So
Yeah.
if the missing dimension is not the key dimension, then we don't need to bother to recover it, right?
Yeah, if it's not key for learning something about your data, then recovering it is going to take more effort, or maybe add more bias into whatever model you come up with, then it's going to help in the explanation, right? The real challenge there is if almost every data point has something missing, right? And then you have to address this head on. And so sometimes it happens. Yeah. Sometimes you just don't have enough data in a certain attribute to build a meaningful model about it, and then you should enforce something. Yeah. All right. So who's heard of cross-validation before? Okay, and who's never heard of this before? Okay, so this is like, you know, so hopefully you see something new, or if you have seen this before, you'll kind of get really ingrained that this is important. If you haven't seen something before, this is super, super important. Okay, so if you're trying to learn, so most modeling of data sets up some sort of cost function that is basically f of this. This is the data, and this is the parameters of some model. And so the goal is to, and the often goal is to find, so alpha star, which is the arg min over all these alpha, given this data. Okay, so this is a common setup. This was true in regression. You can formulate k-means. A lot of the clustering algorithms we talked about this way. We didn't necessarily talk about them the way in this class. This is more common in like a machine learning view of the world, but this is kind of a common setup. And so if you look at this data and you somehow, or this function, and you somehow plot it, this is for all the values alpha, and you kind of did some, this is the f function, then you're going to get something that looks like this, and there's going to be some minimum here, which is the alpha star. And now this curve, this function, it depends on the data x, right? So this is f of this data x here. If there's noise in x, or I were to change f, then this function might change slightly here, right? Or probably is more similar, but it might be like this. And now the minimum, these functions are pretty similar, but the minimum is different here. So that alpha star is different, right? And so kind of this would be of some different data x prime, right? So might be a different minimum. This may give me a different clustering. This may give me a different model of regression. And some of this is due to noise in the data, right? So if x and x prime are data sets which are similar to each other with noise, and I get very different parameters for them of what describing the model, then I should be worried a little bit about what the meaning of this is. If it ends up giving similar kind of prediction, the parameters are different, but the prediction is about the same, that should be, then that doesn't matter so much. But if I get something structurally different, I should be worried about this. Okay? And so, so we need to kind of, how do we deal with the noise in the data when we're dealing with this process? And I want to kind of walk through this with something we've seen now, this, so this, looking at a particular version of this with like, so with like regularized regression. Okay, so we're going to have, so let's look at just like ridge regression here. Okay, and I'm going to have a cost function, which is going to be this data set P, and then I'm going to have kind of two types of parameters. I'm going to have the alpha parameters that I fit, but also some regularization parameter here. Right? So if I remember this cost function, this it's going to be something like the y values of all my data points times the x values times these parameters plus some gamma regularization term times this this regularized or on the parameters. Right? This was this ridge regression model. This was spelling right there, the ridge regression model. And there was a closed form of how to solve for the optimal alpha. So if I fix gamma, if I fix this, so if fixed, then I can solve for alpha star in a closed form. I basically need to take this matrix inverse, setting this up in the right way. Okay, but this assumed I knew exactly what the right value of gamma was. Okay, and each value of gamma is kind of secretly changing that cost function up there in a mysterious way. I don't know how much weight should I put on on this regularizer term versus on this standard L2 loss here. Right, so off that square. Okay, so what I'm going to think about doing here is I'm going to have some algorithm. Let's say I've got an algorithm that gives me an alpha star that depends on a data set x and a value gamma. Right, and this will be some function that I'm going to run on a data set x. This is again the data, and it's going to take in a value gamma, right? And then this is, I've got some closed form thing I can solve for this. Okay, now if I do this, there might be some little kind of noise in the data that can also shift this function back and forth. So how do I, or it could be that it's this value of gamma which is shifting this function back and forth between the red one and the pink one up here. Okay, so the typical way to handle this is to do what's called cross-validation. And the idea is to take my data set P, and then I'm going to randomly, so let's say 70%, map some of the data into what I'm going to call Q, which is going to be the training data set, and some part into R, which is going to be testing. Okay, and this is going to have the X value and the Y value here. This had the X and the Y. So if I have labels, I have separate X and Y labels. If I'm doing clustering, there are labels in there. But this is all of the data. Each row in the data is randomly mapped. Training 70%, maybe testing at 30% here. Okay? And then what I can do is I can now have a, for all for all values gamma, I can solve for gamma star on Q of gamma, right? By running my algorithm on this training data for each value of gamma here. And maybe I don't know, maybe it's a continuous, like the value of gamma can go anywhere from 0 to 1,000, right? So maybe I pick some discrete values and that's probably enough. And then I'm going to evaluate, this essentially gamma star is going to be the arg min over the value of gamma on F, now evaluated on the testing data for alpha Q gamma here, right? Okay, so what am I doing here? I'm evaluating this, the alpha I got from running this function, right? I ran this function for each value of gamma. I got an alpha parameter, and now I'm going to evaluate it here. Or maybe I set, in this case, maybe I don't want to take out the regularizer. I could set this to be 1, or I can set this to be 0, or I can plug in the same value of gamma. And I can evaluate the overall gamma star here, and then I'm going to use the model alpha star Q gamma star. Right, so this makes sense. So I'm going to build a model, but for each value of gamma, this parameter, regularization parameter with Q, the training data, and then I'm going to evaluate how well it works, not based on how well it did on the training data, but how well it did on this held up testing data. Okay, so this is the basic idea of cross-validation. All right, so, yeah, good.
Should it be alpha star inside of the function for gamma star?
Yeah, I used alpha star, yeah. All right, so then this is the overall choice of alpha I would use. All right, so what can go wrong if I don't do this? Yeah.
Sorry, I had a question about your testing data size. So is this just like an elbow function kind of thing where you just have to run, you have to test on data that's of fluctuating size and see at what point it's optimal?
So this choice, are you asking about the choice of the 70-30 split?
Yeah.
So 70-30 is common if you have like a lot of data but not a huge amount, right? And sometimes you do like a 90-10. There are other times when you make it, you want as much trained data as you can, so maybe this is 95 or 99, 1%. And I'll mention this other thing called leave one out, where you build a model on all but one of the data points, and then you test on that one, but you take turns leaving each of the data points out. So you're actually building, if you have n data points, you build n different models. Right, and there are different things different scenarios you can do to use different balances here. You're going to build, you want to make sure you have enough training data, but you also want to make sure you have enough data to test so you know that your choice of gamma was accurate. Usually you need less data for the testing part than you do the training part. But what the balance is, it's going to depend on the situation. Yeah. All right, so, yeah.
Yeah, sorry, but in the formula for gamma star, what are the subscripts on alpha star?
Yeah, and this got kind of small. Let me write this over here. All right, so argmin over gamma of f on the testing data for all of the alpha star that you built on the training data with the different values of gamma.
Thank you.
Okay, so I built, these were, so this came from some algorithm on the training data here, right? So, this gave me some model parameters that depended on Q and gamma. Yeah. Yep.
Will you remind me again what gamma was?
So in this case, it's some other parameter of the data that you might not be able to solve for that one closed form, or like in this case, it's this regularization parameter in this model for ridge regression. You can look at this, for instance, differently if you're doing polynomial regression. Then you want to figure out what is the right degree of the polynomial. It's another good example.
So for linear regression, would it be something like the A value?
Well, in linear regression, I kind of solve for the, once I've chosen, if I'm only considered linear regression, I've restricted to a very specific type of model, and then I've kind of chosen that beforehand, and then I can choose for all the alpha parameters in a closed form way. There's a separate way I'll mention to kind of understand how stable are those alpha parameters. So that requires a slightly different sort of test. This is when there's some other parameter other than the specific model parameters you're typically learning. That's like an extra parameter that's either like this regularization term, or it kind of tells you what class of models you're fitting to. Instead of given that class of models, how do I find the optimal? Usually our algorithms can solve for, the ones we've talked about in class, can solve for some set of alphas, and our algorithms know how to solve for these efficiently. But sometimes they take in some other parameters, like a degree of polynomial, or some regularization coefficient, maybe the number of clusters. You need to come up with some way to evaluate them this way, but that's something that the algorithm doesn't naturally know how to optimize over. Right? So this needs to be like a magic parameter you put in your code. Right? How do I figure out what was the right magic parameter? Maybe you just added it in there. How many iteration steps do I run gradient descent? This turns out this is actually a parameter of the algorithm. And so you often don't want to run gradient descent all the way to completion, like if you know what gradient descent is. Okay. Okay, so what goes wrong if I don't do this cross-validation to choose this gamma parameter? What if I just evaluated the gamma parameter on, say, Q, or I just built the model on all of the data set, and then I evaluated the gamma parameter on the model I trained on all the data? I didn't separate this.
No, because that way, when you test those kind of prediction, then it will just be 100% because you build up your model using those data.
Yeah, so this kind of I'm building up the model using this data. So if the model has the data has an abnormality where and it happens to work better with a certain gamma parameter, then yeah, I'm kind of secretly biased toward choosing that. Whereas this is kind of factoring any peculiarities that have somehow secretly affected this training out. I factor that out, right? I'm kind of evaluating it separate from how I'm doing the training. Kind of a different way of seeing this is that almost all of the analysis in data mining and machine learning is built on this idea of data that comes is coming IID, right? There's some phantom process. There's some, overall, like this is all data, and as I observe data, it comes in IID into this data set. Each row is an independent and observation from the same mystical model of the real world that I'm somehow observing in some way. And so these are coming in IID. And so if you kind of look deeply at the analysis, this is kind of baked into anything we looked at. It's this secretly has assumed this about, we're trying to predict something about the real world, which we don't observe, we only observe some data, but we have IID observations from it. We can treat them each as an independent observation, and they're all telling us about the same phenomenon here. Okay, this is baked into everything that we analyze here. And so the goal is not to say how well did we do on this data, but how well do we think we're doing on this data here. Okay, so what we're doing is we're secretly sending some of this into a testing part, and this, because it was split randomly here, then this is also essentially IID data from this unknown distribution. So I can say, I can build a model, and then I can say, okay, if I got new data from this IID distribution, how well would I do? And so this held out data is a proxy for this unknown distribution, as opposed to the data we actually observed. And it allows us to separate these two things. Okay? So this is the right way to think about it. This didn't really, okay, let me mention, one of the things this leads to is, in addition, so for cross-validation, there's two purposes. The first one is to choose these parameters that we can't like automatically fit with an algorithm. But the other one is to predict to predict what's called generalization. That's saying if we got, this is basically saying if we saw new data, how well will our model do? Right, so if I get new data from the same mystery source, how well do we think the model we found is going to do on this new data? Right, that's kind of the point, right? We have the data we already have, so if we want to look up some customer, we want to say, okay, how are they going to act? Well, we've recorded how well they're going to act, right? So we don't need to predict that or categorize that. We want to predict what we're going to do on new data we haven't seen yet, right? This is kind of the whole point of analyzing the data we have seen so we can do something new in the future and make money, understand kind of how scientific process is going to continue to happen as we see more data or as kind of a general theory about something, right? And so we have some model and we have some way of measuring a cost associated with it. And so if we want to know how well we're going to do with respect to our cost function on new data, then we can also use cross-validation. Now, it's not fair, again, to predict generalization by building a model on this data and then say, how well did the model do on this data? There's kind of some inherent bias. I chose the model which happened to do the best on this data, right? But maybe there was due to some randomness in this data from the IID sampling that caused this model to do so well. So if I do a split to a training and then I evaluate on the test, I expect I'll do worse on the test data. I should in general do worse on the test data than I did on the training data. This was highly optimized for the training data, but the testing data is kind of a reality of what's going on.
So you're always putting in these new values into the testing data frame? Is that in general?
I'm always doing what?
Taking these new observations and you put those new observations into the testing data frame from the streaming standpoint?
Yeah, so I mean, you don't even necessarily think about this as streaming, but I'm splitting the data I have randomly. You could do this in a stream where the first part you build the model and the next part you do the testing.
Also, it's random. We're
But-
not actually putting the new observations into the testing data.
Yeah, every data point I randomly put into one or the other. Sometimes in practice, people often to put this first 70% here and the second 30% here. Sometimes that adds some weird bias because it's not actually IID. The ordering might change, or maybe it's pre-sorted. I did it by, scanning I sorted the data alphabetically, right? And maybe there's more people whose names start with A happen to be taller because they come from, ancestrally, they come from a country that is taller than people who start with B's, right? So anyways, there could be some weird things has to do with the ordering of the data. So you should really try and split this randomly if you can. Sometimes it doesn't make a difference, but sometimes it'll cause some bias. Okay, so you should keep these two things separate, but yeah, so these are two different things you can do. Now you should not use the same testing data to choose parameters and to also predict generalization. Okay, you should actually, if you want to do both things, what you should do is have some, so you have, say P, and then I'm going to randomly split into 3 buckets now, Q, R, and S, where say some data is randomly going to Q, some data is going to R, and some data is going to S. Okay, so now I'm going to I'm going to then train on Q. Let me write this more clearly. I'm going to train on Q. I'm going to choose the parameters on R, and then I'm going to look at the generalize on S. So I'm going to predict generalization on a different held out data. Okay, yep.
So when I'm choosing the Q and R, should I do it like multiple times and average out so that just to get a better estimate for that particular parameter?
Yeah, so if you have enough data, so it depends on how much data you have, right? So this is really a technique that grew out of the modern age of computers and large data sets. These ideas, I mean, they date back to statisticians a while ago, but they really took off when people started to say, I have lots and lots of data sets, and I can use computers to automate some of this for me. Which I think became popular. I think for instance, there was a big push out of the statistics group in Stanford, I think in the 70s and 80s about doing this. It's been around longer than that if you trace things back. And then in machine learning and data mining, I'd say the 90s is when this really exploded as the dominant paradigm for dealing with parameter choosing and evaluation. Okay, and it corresponds with the area you have lots and lots of data. And so in that case, you assume that the data set is so big that you have enough data to train on just in Q, enough data to test on to choose parameters just in R, and enough data to generalize just in S. Okay, that's not always the case. People have said, okay, let's go back and look at smaller data columns, or maybe generally statistics is a better fit. And in that case, you need to be more careful what you do. And you might say, I'm going to go back and do this split several different times, and the output of many kind of randomized trials over this, right? Sometimes it looks like this, and I'm going to estimate some parameters this way, multiple trials here. And this is a reasonable thing to do if you don't have quite as much data, right? And I mentioned this leave one out where you make it so the parameter choosing set or the generalization choosing set is always exactly one data point, but you take turns which data point it is and you average over those. And that's a safe way to do it. It takes a whole lot longer to do that, right? Because now I have to run my training many, many times. So if your data is big enough, you only need to run your training once, right? If your data is small, it doesn't take that long, hopefully, to run your training, and then you can tend to do it multiple times, and you get a better estimate of both the parameters and also the generalization. Right? So it really depends on how long it takes to run and how much data you have, and how much you care about being that accurate. Which, if it's like life or death situation, you're going to do as much as you can. If it's like, you know, I'm gonna predict something for on the Jazz game tonight. You know, I just want to make a guess. I'm just going to run it once. It doesn't really matter, unless you've bet your life on the game. I'm not recommending doing that, but just okay. Yeah.
So it seems that it's based on the quality of the data set, not only based on the size of the data set. Right, because if the data set is like relatively like small but cover like some kind of like almost all cases or not cases but cover like different aspects, so that model will just be like even better for larger like similar data.
Yeah, so this is getting to a point I want to get back to on bootstrapping, which I'll mention soon. But in most cases, it does not depend on the quality of the data. Basically, you're going to get worse generalization error if your data is lower quality. You're going to say, well, when I see new data, the data is super noisy, it's not very good quality, I'm not getting a great model, because when I test on new data, it doesn't do as well. I don't necessarily need more worse data to tell me that it's not going to do well. If it doesn't do well, then on the data I see, it's not going to do well. Right? So it doesn't really have to do with the quality of the data, it's just the amount of time I'm willing to spend on training or running my training algorithm multiple times, and the amount of data I have. How much do I trust this process? This is kind of a random process. Remember, like these Chernoff-Hofting bounds and like these coupon collector things we did at the very beginning of the semester. Those convergence results don't depend on the quality of the data, they just depend on the number of data points. Right? So if I can get 1,000 things here, or even 100 or a few hundred, I trust this really pretty well. If it's even 20 or 30, maybe I don't trust it that well, and I might want to do some repeated trials. That's kind of the calculation you should be doing in your head. All right. Okay. So what happens if we don't do this? So let's give an example. So who's ever played with like these data sets in Kaggle? Right? Who's done some Kaggle or looked at Kaggle stuff? Right? And Kaggle is just an example, but there are these data challenges online where often what you're presented, there's some variations of this, is that you have, as the user, you're going to see some data X and Y. This is data set, say 1, and then you're going to see some X values, and you often want to predict the Y values. So you're building a model. You're building a model from X to Y, right? You try and build some model like this, and I get this unlabeled data 2, right? And so I want to predict these Y, and and this is kind of the interface, and then behind this interface here, there's this is what's seen by the user. There's this, I can submit models across the interface, and they give me back some score of the accuracy. How well am I doing? Right, and so behind the interface, they have the matching labeled values on this unlabeled data set too. Okay? And so one thing you can do if you just want to do well on Y, they often limit the number of models you can submit, because I can just keep submitting random models and hopefully one of them is going to do well. Right? And so there's usually this, while it's active for a while, they have this leaderboard on how well different groups are at submitting models, how well they can do on the score. Okay, and you can keep submitting models and think of these as just choosing, searching over the parameter space, kind of maybe even naively, maybe a little bit intelligently here. Okay, so often what they also do, they'll have a time limit on this where they run this actively, and every day they process results and pull scores, and then at the end there's this data set which has the XY. Data 3, and at the end of it, they post, everyone gets to submit one model, and they post the score on this data set, which has been completely hidden. Okay, that's because if you don't, what happens is you get some groups that will have figured out ways to score really well on data set 2, and then do horribly on the third data set. This is not that uncommon. And what they're doing is they're kind of overfitting these parameters to using this interface to kind of learn the values of y without actually learning a good model that generalizes down here. And so this is what they've done. And what you should do as a practitioner is you should learn the parameters on the second data set, and then hopefully that will generalize on the third one. But there's been some groups that have published research papers on how to randomly send like different predictive models just using the first and the second data set that gets you to the top of the leaderboard that basically does as well as, that ends up doing as well as random on the third data set. And so people know how to spoof these competitions, and that's why they need this third hidden data set at the end. So if you heard of this, like this Netflix challenge that came out, like I think it was over a decade ago now, and we'll talk about that on Wednesday. They used this model, and this was essential for kind of preventing this sort of thing. And the challenge worked so well because they kind of knew that this might, they kind of had in mind that this sort of stuff might happen. It wasn't quite exactly this model, but there's variants of this where you need to kind of keep the choosing parameters separate from the generalization. Okay, so this also happens this can happen in like ways which are less benign than these Kaggle competitions, which are basically just for fun. Sometimes there's a prize. But like there are these famous data sets in machine learning, like this CFAR data set and so forth, and like in computer vision, this is very common to have these data sets, and they've been engineered to death, right? People have developed models that work really, really well for those data sets to the extent that they do not generalize beyond those data sets anymore. Now, sometimes they do, like some of these deep net models have ideas that generalize better, and those tend to generalize because we have these large enough data sets like ImageNet to train on, but a lot of these old machine kind of computer vision data sets where they're trying to segment a seam had been over-engineered because they just put the whole data sets out there and people set it up the wrong way, and this is part of how we learn that this was a problem. This can also happen, but you can think of like from a scientific perspective, if there's a fixed data set that you're trying to make a scientific discovery about, and the data set's out there, who's to trust that you actually perform this correctly? Right? When you publish a paper, how do you know that you actually separated the training of the parameters from the generalization prediction? And not all papers do this, but you should be doing this in the correct way. Otherwise, you're not really reporting an honest result. Okay, so you really need to keep your generalization error separate from your training, and that includes choosing parameters as well. Okay, let me more quickly go through a few other aspects here. So there's another related concept called bootstrapping, and bootstrapping is one of these overloaded words that means a dozen different things. I'm referring to the one by Efron 79, but this is the idea that maybe I have smaller data set that is not a great data set, but it happens to fit to kind of, I can build a really good model on it. And I think it's just the right data set. Or I don't know how much to trust the data. I kind of have, again, I have this cost function, and I have these alpha parameters. And how do I know if I have a data set that looks like this, and this was, say, the cost of this data set, X, or if I have a noisy data set, f of x prime. If I add noise to it, is it going to change the minimum from being here to here? Maybe this difference in the parameter space is big, but maybe it doesn't affect how well it actually does on new data very much. Because if I were to map this pink one back onto the green thing, onto the red curve, well, it's going to evaluate pretty much correctly on the red curve. Basically the same as the minimum there. So if I somehow ran it on the pink one, and even though the parameters are very different, how well it generalizes isn't going to change very much, right? If the red is a true generalization score, right? Can I tell the difference between? But if the pink was a true generalization score, right? And so I ended up with the red model, then this difference is actually pretty big, right? So, depending on which one is the true one, these are very different points of view. Okay, so how do I assess how good is my data? How much should I trust the data in the model? And there's a similar idea called bootstrapping, where I take P, and so with generalization, I'm basically doing sampling without replacement. Each data point goes to exactly one test set or one training set, typically. Okay, that seems to be the safer way of thinking about it. In bootstrapping, I'm going to instead pick a bunch of these. So I'm going to say Q1 here, and I'm going to, I'm going to sample. So this is going to have n data points in P. I'm going to sample n points ID from P. So this means with replacement into Q1. Okay, and now I'm going to repeat this for Q2 and Q3 up to QK. So I'm going to create not just one data set of size n, but k different data sets of size n. And they're all going to have exactly the same size as P. Okay? So now instead of saying, well, if I did training data and only 70% of my data, I know roughly how well I can do if I only use 70% of my data. This is saying, how well do I do if I use all of my data, all 100% of the data. And I also can look at this variation across these k different data sets and say, on average, how are they doing? Right? So if I do this, I have this one pink one here, but I build right, all these different kind of each of these models is giving me a different answer, and I can kind of see the variation across these different models from these different data sets. And I can kind of understand how stable this learning process is without sacrificing something about the size of the data or about kind of, if there was one data point that was really important, well, in some fraction of these generated data sets, I'm not going to sample that one, I'm going to miss it. Right? So how general, this only works if you assume, again, this is all coming from some, again, unknown IID process, and then these are a better simulation of IID training data than if I just chose one of these. Right? And this kind of helps you get to your question about how do I know how good my data set is. And this is a bit better way to explore this sort of thing. You can look at then the variance in the quality of the solutions is the typical thing people look at. Okay, so I just want to mention this bootstrapping isn't kind of a separate thing, but it's a similar sort of resampling concept. Okay, so that was kind of the cross-validation and bootstrapping. Any kind of general questions on this? This is like super important. Yeah.
How well does bootstrapping with, say, K data sets compare with K-fold cross-validation?
Right, so bootstrapping is going to be slower because you're going to need more, you're going to need to run your training algorithm on size n every time. Where K-fold cross-validation is like I'm maybe taking 90% of my data every time. And so it's going to be a little bit faster to run on that. Usually not dramatically so. Bootstrapping is a little bit more accurate in that I can do cross-validation on each of these data sets now in full. And it's going to give me a sense of if there's some data point that is really essential, if I'm really sampling these IID, how much should I trust, if it's really dependent on this one data set, basically it's going to wind up in roughly 2/3 of these data points. And so I'm going to do, it's in these K data sets. And so, it's going to kind of test it a bit better. The main difference, this will kind of show up in K-fold cross-validation, especially if you randomize how you do the subsets there. So K-fold cross-validation is like you build a test set, you divide your data into K things and you build K test sets, and every time you train on everything except that one test set. So you do this K times. So the main difference is that the value of n you're evaluating, if you really want to know, I have n data points, how much did I get out of n? If I use 90% of n because I did 10-fold cross-validation, I'm kind of building on less data. So if I have a huge amount of data, it probably doesn't change that much. If I have 10 data points, then this is more important to get this right. But if I have 1 million data points, probably doesn't matter so much. Yeah.
So the distribution, the original distribution, like the one that P, where P was taken.
Yeah.
Okay, is that the same distribution for K1, K2, K3, and K? It's the same.
Each one individually you can think of as then being IID from there. It's not exactly true because you're going to get some data points are going to be in here twice.
Yes.
Right. So it's not exactly ID. You're adding some more autocorrelation in your data set. So it's not exactly the same thing. It's not completely ID, but it's a reasonable approximation of it. And so there's a lot of work on understanding how close this is. If you have enough data in every case, they all converge to the right answer. If you don't have enough data, then in different cases, this is better or cross-validation is better in converging because of the with replacement and the without replacement set. And you can look at it depends on the data set which one is more, the sort of analysis you're doing, which one is, for the data set size you have, gives you a better approximation.
So do we have bounds for this, like using inequalities like Chernow-Hopkins?
Yeah, you can go through that and get some bounds. There are multiple ways to get bounds and multiple sorts of analysis on these. And the differences are pretty subtle. I actually don't know all the differences between them. But even if I did, I don't think I would, I didn't think it was worth looking up to tell you at this stage. I mean, that would be like, it would take really a quarter of a semester to go through and explain the subtle differences in these, I think. Okay, good. So I want to tell you a little bit about outliers, how to deal with outliers. We have 10 minutes. May I need a little bit more time, but I don't think I need that much more time to really go through the basic premise here. And so, so the basic idea with outliers is that you're going to be given some sort of data. You're going to fit some model to the data. It could look like regression, could look like dimensionality reduction, it could be clustering. So if this was clustering, then instead you would think that the data would look like this, and maybe it was k-means clustering, so then the model is then going to be these points, right? Where I have M is the model, and the blue is the data. Okay, so there's this general phenomena that we've kind of been talking about throughout the semester. Okay, and so an outlier, an outlier is a data point that is not fit well by the model. Okay? So I can look at the residual of every one of these data points in either case, right? Usually the cost function is decomposable, so it's basically a sum over the costs associated with the fit of any data point onto the model. And I'm kind of adding these up typically, right? But the decomposability means that if there's some data point which does not fit the model, there's some data point out here, this might be an outlier for either of the cases, because either the residual to the regression line or to one of the clusters is pretty big, right? So that's kind of how I'd like to think of what it was an outlier. Okay, that's how we can more technically define how to think of an outlier. Okay, so this basically implies a fairly straightforward algorithm for trying to get rid of outliers, right? So then this implies some algorithm for, let's write this for an algorithm for outlier removal, right? So this is one. I'm gonna fit a model. I'm gonna calculate the residual. Then I'm gonna remove X in my data set if the residual is too big, right? So I just build the model, calculate the residuals. If that residual is too big, I label that point outlier and I remove it. And then maybe I want to go and refit the model again. Okay, so, this is kind of the main natural way to deal with outliers. Now, this isn't the end of the story. This does not always work. There are two issues pulling this in either direction why it might not work.
So what if the model chose, for instance, with your clustering one, that the center was the outlier?
Yeah, right. So in clustering, for instance, in case center clustering, I would have chosen this as the center of the cluster, right? So then I wouldn't have removed it as an outlier, right? And so that's not going to work so well, right? And in regression, it could pull the curve pretty far, so I can't tell this outlier from the actual data points. Okay, so this often works, like in regression, or if I have a more robust clustering, like k-median clustering. I'm typically not going to put the centers at the outliers, and then I can remove them. Then I have a pretty, or if I do if I have a good regularization term in my regression, or the outlier is totally extreme enough, I'm not going to fit it, then this will work. Or if I do a regression that minimizes the L1 error, right? There are ways you can set up an optimization problem to solve this. Then it should not be very affected by outlier. Or I use one of these robust things like the what's it called, the Siegel estimator, or this other one I mentioned, right? Then it should be robust to these outliers if it's based on like the median. Okay, but if I did that, then I already have a good model. So then why do I need to remove outliers? If I could already fit a good model, if the model is good enough, then why do I need to remove the outliers in the first place? If the model could not deal with outliers, then how do I trust the model to be able to remove them, like in clustering? Right? So this is the most common thing to do, and often, like in regression, if the outlier is extreme enough, you can still see it, right? You're gonna pull the regression model a little bit, but not all the way away from the data, and the outlier will still be apparent, and that its residual will be way higher than everything else. Right? So this sometimes works, but it's not really a panacea. There's lots of these other cases you have to deal with. Okay, so there are these other approaches, and so in the clustering example, like what could you do? If I have an outlier and it's the only point in the cluster, right? Because I put a cluster center there. Well, then that's probably an outlier, right? So there are these kind of tricks you can do. What if there are 2 points in the cluster? Maybe if they're both outliers. What if there are 10 points in the cluster? Yeah, then maybe they're outliers. Maybe that's actually a cluster, right? You know, it's at some point there's this gray area, right?
Well, it's basically like depending on the size of your data set, right?
Yeah, it depends on the size of the data set. Okay, let's say I'm going to fit a model, and then I'm going to remove the 10% of points that have the largest residuals. So even if my data set is big, I remove more points, but I still have 90% of the points. If I have a lot of data, that's still enough. Then I fit a model again on the remaining 90%, and maybe I again remove the 10% for this residuals, right? At some point, this has to stop, right? Like if I think about a Gaussian distribution, right, a typical distribution of noise, you know, I can say that basically with one standard deviation, I basically get, and here I basically get 2/3 of the points. If I go out to basically 2 standard deviations, then I'm going to get something like, this is going to have like 95% of the points. Right? If I go out 3 standard deviations, I'm going to get 99% of the points roughly. But if I have a big enough data set, there's always going to be some outliers, but maybe they're part of the Gaussian distribution. Maybe they're just naturally part of the distribution. Right? So if I remove them, is that going to help me fitting my model? Maybe. Maybe not. Right? So there's a bunch of heuristics you can do like this, right? Like removing some fraction of them. I'm kind of running out of time. If you leave, that's okay. I'll list a few things here quickly. One thing to do, there's various things based on the density of data. Sometimes data varies in density. You could have some really dense clusters and then a more spread out cluster. So this is a little bit tricky. So what they might do is like the what's called the reverse nearest neighbor, where I look at a data point and I find, say, its nearest neighbor, or it's, say, the distance to its kth nearest neighbor. Kth nearest neighbor. And then I look at this point and I look at its kth nearest neighbor going back again. And if these are roughly the same, it's probably okay. It's in a less dense region. It's probably okay. If those are very different, then that's probably an outlier. So this is a pretty good way of doing it. What's called the reverse nearest neighbor. Right? Where if I have some good metric, I can look at how far it is to like the 10th closest point or the second closest point, and then look at that second closest point and look at the distance back. And if those are within a constant factor of each other, 2 or 3, probably not an outlier. If they're off by 100, it probably is an outlier. But you don't always have a good distance metric or a good, something else to do like that. One final thing I want to say is that in addition to like the Gaussian, this function, remember, is if I have a center mu, this is e to the x minus mu squared. So that means as I get further away from mu, the mean, it's decaying exponentially. The probability is going down exponentially. But in real life, there are these things called these heavy-tailed distributions. And these are things that decay polynomially. So an example is like Zipf's distribution, which often looks like the ith item in Zipf's distribution is going to be some constant times roughly 1 over I, often to the power alpha. So it's going down in a polynomial way instead of in an exponential way. Okay, and so for instance, the frequency, I used Fi because the frequency of words in the English language are roughly Zipf distribution. The word a occurs roughly, I think the occurs 7% of the time. Yeah, of, so the is roughly 7%, of is roughly 3.5%, and is roughly 2.8%. And basically, if you sort the words by frequency, they're decaying polynomially. So there's a really heavy tail. It doesn't decay exponentially. So you have a lot of stuff, maybe a lot of a non-trivial 10, 20% of all words are things that occur very, very rarely. And this makes it hard to filter out outliers. It's easier to think about this in text, but this could occur with like spatial data as well. So like Amazon made its business on selling kind of books that you wouldn't find at a bookstore. That's how they initially got off the ground, and this kind of allowed them to scale out in ways. And so a lot of businesses nowadays are reaching this heavy tail of customers that you can't get at like small localized or specialized stores. Right? So do you really want to throw away these outliers at all? Maybe you want to study them and deal with them separately or figure out how to model them and work with them. Right, so this outliers is an extremely gray area, and there are some simple heuristics that work reasonably well for extreme cases, but in a lot of cases, you may not want to actually try and filter them out. Okay, so I'll kind of end there, and we'll talk about privacy and issues with adding kind of noise and data on Wednesday.